here. Okay, so we are recording now. So again, so this is what we are dealing with. We are trying to figure out how do we estimate the counterfactual based on this slide. And this is where the Ezra Howard tutorial that I shared with you comes into play. And then this is, so what I want to do next is I want to go to our Canvas page and open up the Howard tutorial here. And you guys have access to it. You guys have read through it. So this is great. Or at least you've read through 3 pages of it. Let me go ahead and. Is everybody able to see the Ezra Howard tutorial? Give me a thumbs up real quick, maybe. Okay, perfect. That's good. So in this tutorial, it gives you a lot of examples, different ways of figuring out. And so what I want to do today is I want to get started on the idea of how we estimate the safety using the empirical Bayes method. So I want to read through from here and then take it from there. The task is to make joint use of 2 clues. Can everybody type up what are the 2 clues on the chat box for me? What are the 2 clues we are talking about here? Because our task is to make use of the joint 2 clues of safety of an entity. They say that right in the next sentence too, if you read through this, the crash record of that entity and crash frequency expected at similar sites. Okay, so I know I asked you to type it up in the chat, but it's no fun when it's the right next sentence. But this is the idea, right? So we are trying to combine these 2 estimates. And typically, when we are trying to combine 2 estimates, one good way of doing that is through a weighted average. Okay, so we are going to do a weighted average of the crash record of that entity and crash frequency expected at similar entities. Okay? So this is the formula for combining the 2. So this is what you want. This is your capital B that I showed you in that slide. So this is your capital B. And then this is weight. We'll figure out how to get that weight, and crashes expected on similar entities. So this is the part that comes from SPF. Okay, so you applied the weight to the crashes expected on similar entities, and then you add plus 1 minus weight. So this is how you do the weighted average, right? So W1 times something, and then 1 minus W times something. So 1 minus weight times count of crashes on this entity. So this might be average of 3 years, or this might be count for 3 years, or whatever. And the weight is a number between 0 and 1. So let me ask you this. Based on this equation, if you assign the weight to be close to 1, what is the implication of assigning a weight that is very close to 1.0? What are you saying if you're using a weight that is very close to 1.0? Let's say something like 0.9. So I'm going to type that question up in the chat, and I'm going to look for some responses here. What are the implications of using a weight as high as, let's say, 0.9? Okay? What are you saying? You're doing a weighted average, and you're assigning one of those things a weight of 0.9. What does that tell you? And feel free to either type it up in the chat box or raise your hand, and I'll be happy to call you on it, and then go from there as you can respond by voice as well. Okay, anybody wants to take me on? Okay, I see some chat messages here. Okay, so I'm going to kind of quickly look through that. similar to the other studies? Yes. So basically what you're doing is you're relying very heavily on crashes expected on similar sites. I know this text actually says accidents, but I would still like you to use crashes. I know it's an old paper, so it still uses the term accidents. Anytime you're talking to me in this class or anybody else about these traffic stuff, use the term crashes, please. But anyways, you guys are correct by and large. You're weighing the crashes on similar entities a very large amount. When would you want to do that? You would want to do that if you have a lot of faith in what you're getting out of the similar entities. Okay, so when you have a lot of faith on what you're getting out of similar entities, that's where you want to assign a very large weight to the data, the information that is coming out of the safety performance functions. Okay, so because crashes expected on similar entities will be from a safety performance function, so that means you're assigning a lot of weight. So for that to happen, your standard error of that safety performance function has to be very low, or you don't have a lot of confidence in your own site's estimate. So maybe your site only had like one crash in 3 years. So it's very low precision value of your crash estimate, or your site is has only like 1 year worth of data. So your weight has to account for all of these things. So if you wanna have a weight that relies on the reliability of your safety performance function, but it also relies on, or maybe somewhat be inversely proportional to, how many years of crash data you have and how many crashes you actually have from your own site. Okay, so how do we estimate this weight now? So there is actually a formula for weight, and we'll get to this abridged or full later on, but there is actually a formula for weight that comes in. And the formula for weight is right here. And I know it's kind of tucked into the text here, but I will try to, maybe I should just open it in. Just download this. So give me 1 second here. I'm going to go ahead and open it in PDF so I can highlight certain things. I know you probably can't see it yet, so I'm just going to go ahead and stop share. And I'm going to go ahead and share my entire screen, at least PDF here. Okay, you should be able to see the PDF now. Give me a little thumbs up via Zoom, please. If you're able to see the PDF, please give me a thumbs up. Okay, perfect. Thank you. Okay, so all I need to do now is figure out, okay, how do we estimate the weight? And the weight is estimated using this formula right here. I'm going to go ahead and highlight it. Okay. So the weight is estimated for a roadway segment. The weight is estimated using this formula, neta times 1 over neta divided by phi L. Okay. And what are those parameters? I'm gonna let you in a second, but let's see. This is the formula here. L is the length of the segment. Okay, L is the length of the segment, and neta is the expected number of crashes for that segment. Expected number of crashes for that segment that is coming out of the SPF. Okay, and then phi. So mu is the number of crashes for expected for similar segments. Okay, so sorry, mu is the number of crashes for expected on similar segments, and crashes per year expected for similar intersections. Okay, so now there is a 2 different formulas. So there is like a little bifurcation here, because there is one formula for similar segments and one formula for similar crashes. Okay, and the big difference is the unit. Okay, the unit is crashes per kilometer year if you're talking about roadway segments that are continuous segments of some length. Okay, and crashes per year for one intersection site. Okay, so mu is the number of crashes expected on similar crashes, or crashes per year for similar intersection. And where is this mu value going to come from? Is it going to come from your own site or is it going to come from SPF? So here is my question for you. Does mu, this value that I'm highlighting here, this mu value, does it come from SPF or does it come from your own site or site of interest? So SPF or site of interest, which of these two is the source of the value mu? Give me the answer either in the chat box or raise your hand. Does this mu come from SPF or does it come from your own site, history of your own site? SPF, remember, is the safety performance function that gives you information from similar sites. Okay, not seeing any responses, so that's not good. See, let's look at the definition again. The number of crashes for expected, so you can get rid of this for, okay, so we can just cross that out. The for shouldn't be there. The number of crashes expected on similar segments and crashes expected for similar intersections. So anything that you see from similar, that is going to come from SPF, safety performance function. So anything that is about similar entities, that will come from SPFs. So the answer to my question would be SPF. Okay. NETA actually comes from your own site. The number of crashes during a specified period given by, no, actually, no, this is again a variant of mu. So NETA is the number of crashes expected during a specific period given by mu times L times Y, where L is the length of the segment and Y is the number of years that you have data for. Okay, so mu, if you multiply mu with L and Y, you can get this NETA, okay, for similar segments, and mu times Y, because obviously there's going to be no length associated with the intersection. So you can get rid of the L in the formula, and mu times Y is for similar intersection. Okay. And then phi, this phi value, the last one, is the over dispersion parameter. And anytime you have a safety performance function, there has to be an over dispersion parameter that needs to be provided with that safety performance function. That needs to be provided with the safety performance function. Yeah, so say phi is the over dispersion parameter. Estimated per unit length for segments, and then and it's unitless for if you're talking about that is not estimated. So estimated parameter for unit per unit length for segments, normally entities for which the crash frequency is not proportional to length. For example, intersections or rail highway grade sections have an over dispersion parameter that is not estimated per unit length. Okay, so does that make sense? This phi value is the over dispersion parameter, and the unit for this would always be per unit length if you're talking about segments, and it would always be unitless when you're talking about intersections or something. Right, and I see that Megan did have the right response of SPF in there that I did not see earlier. So thank you, Megan. Okay. So now I think the best way to understand this is through an example. So that's the example we are going to do. And what I want to do this example on is a sheet of paper here so that you can follow along. So give me 1 second. I'm going to try to set that up for you. So this is the example we are doing. So I'm going to go ahead and highlight this example. And in the meantime that I'm setting this up, what I want you to do is I want you to make sure that you guys have this open on your computer screens if you could, or you can follow along here as well. But let me, if you guys give me a second, I will just get this set up on so that we can actually do this problem on a sheet of paper, and we can look at the formula and everything. So I'm going to go ahead and pause my recording for a second. And in the meantime, I will just get it set up to record on a sheet of paper. Okay, give me 1 second. So is everybody able to see the notepad in my hand on the screen, everything? Give me a thumbs up, please. So you might have to pin the video from iPad on your screen, please. So go ahead and do that. And then I will start writing stuff on it. I think it's upside down. Okay, that's not good. Oh. Oops, yes, it is upside down. Oh, why is that upside down? I don't, okay. I did try this. Let me switch camera. Maybe there's a setting on the iPad that I show self view. Man is good. I'm not sure. Why is it showing upside down here? Let me see if I can switch the camera now. Okay, this seems right. Yeah, this is perfect. Okay, finally, yes, I was using the wrong camera there for a second. So this seems good. Okay. So we can go ahead and get started on the problem now. So everybody should have the iPad screen as pinned screen. And what I'll do now is that I will go ahead and look at that problem statement that we were dealing with. And our problem statement was a roadway segment is .8 kilometer long. Okay. ADT is 4,000 vehicles per day. 12 crashes in last year. Okay. And then, so this is all about your site right now. Okay. So this is from your site of interest. That's the information coming from. And then you have some information that's coming from SPF, or what we'll call the similar sites. The similar sites information. And from similar sites, what have you learned? That your expected crashes, or mu, is equal to 0.0224 times ADT raised to power 0.564. And the unit on this is crashes per kilometer year. Okay, so this is the facts. So one piece of information that's still missing is phi, and that is equal to 2.05 per kilometer. So this is all the given information that we have. And now what we want to do is we want to see if we can, we are able to estimate how many crashes to expect on this site over the next year, right? And remember, there are a couple of things happening. We only have 1 year worth of data. So that's not a good sign. That sort of automatically tells me a little bit that I will probably have to give more weight to the SPF information. That makes sense? Okay. So let's see how we solve this problem. So remember all this information that is a given. And now we are trying to figure out, okay, how many crashes would it have? So I will just go back to my formula that I shared with you earlier. So our formula is that, yes, we are going to have some weighted average of this 12 and some number that comes from this. So first, let's figure out how many crashes would you expect from this site in 1 year period. So now I want you to have your calculators out for me, please. And what we'll do is we'll do mu equal to 0.0224. And what is the ADT? ADT is 4,000. So I'm going to multiply that by 4,000. And I'm going to give it raised to power 0.564. Okay, and I want you to use your calculators for just 1 second here, one quick second, and figure out what is the value for mu based on other similar entities. And if you're not able to figure out how to do this, what I want you to do is leave either a comment in chat, but it should be pretty straightforward. All I'm doing is plugging in 4,000 into the formula that is given into my SPF. And remember, this is my SPF, safety performance function. So does anybody have the number for me? And maybe I will do that practice as well, right here. Does anybody have the number? We can use our calculator too. Okay, 2.409. So I'm just going to take your word on it, Katie. And let's see if there are some other numbers. 2.41. Yeah, that's probably right. So let's go with 2 decimal places. 2.41. And what's going to be the unit here? What's going to be the unit? Don't forget the unit. So anytime you're giving me the answer, think about the unit as well. What is going to be the unit, please, on the chat box, please? Crashes per kilometer a year is exactly right. So you expect, okay, that's correct. Thank you very much, Katie. And I think there were other students, Alexander and Cody, thanks for the number. And Alexander, you gave me the number as well. Simon, thank you for the number too. So this was great. So you guys figured out, but the key important thing is the unit now. And now, if I had more years of data, then I'll convert this number into whatever number of years data I had. But remember, my site only had 1 year worth of crash data. So I'm just going to have to sort of say, okay, my expected count is just going to be based on the length of the segment. So if I want to get like, okay, so expected crashes on an 1.8 kilometer segment. So if I want to find the expected crashes on a 1.8 kilometer segment, and where am I getting this 1.8 kilometer from? I'm getting this 1.8 kilometer from the length of the segment, because my segment is 1.8 kilometers. So I need to figure out, okay, how many crashes do I expect on a 1.8 kilometer segment? I expect 2.41 times 1.8. That's how many crashes I expect there. So I will just do 2.41 times 1.8 on my calculator, and I will figure out, okay, it's going to be about 4.34 crashes per year. Is everybody clear on this? 4.34 crashes per year. So now my expected number will be a weighted average of the number 12. That's the number of crashes I had over the period of time, over last year. And then I will, and 4.34. So somewhere between 4.34 and 12 lies a sort of empirical base estimate of how many crashes I should expect on my site in 1 year period. Okay, so how do we get that? We need the weight. And remember, the formula for weight for us was, formula for us on the weight side was, I'm going to write down that formula, is W equal to neta Okay, so that's the formula for the weight here. Okay, L is the length of the segment. So is number of crashes. I'm going to go down here. So I'm just basically making sure that we write down what each of these terms in the formula mean. They were provided in the paper as well. So if you can always refer back to that. Crashes that's the number of crashes during the specified period. And how do we know what is the specified period in this problem? The specified period would be known based on how many years of crash history you are given for your own site. Okay, so the specified period, so I'm just going to highlight what is the specified period. The specified period would be the number of crashes. Specified period would be the number of years your site has crash data for. Okay, Neta is the number of years your specified period, number of years your site has crash data for. So in this example, that would be 1 year period. Okay? And you could get this value by doing mu times L times Y. And in our case, we already did some of that. We already did estimate that. So it was going to be 2.41 times 1.8 times 2.41 times 1.8 times number of year, that is 1. Okay, so 1 is the number of year, Y is the number of year. So I got that. Okay, and then phi is my over dispersion parameter, which in this case is 2.05 per kilometer that we saw that was given in the problem. Okay, so we know the phi is the over dispersion parameter. And that is equal to 2.05 in this problem. And the unit for that is per kilometer. Okay. So now we have all the entities in that weight formula. So we are ready to apply the weight formula here. So we'll go ahead and do that. So the weight is the weight formula. So when you apply the weight formula, so let's do this. So there is another little weight formula that is given in equation 2. So if you can rewrite that. So if you look at the equation 2 from the Howard tutorial that provides the weight formula. So W, and that basically comes from simplifying the one that I provided you earlier. So if you do that, W will be equal to 1 over 1 plus mu times Y over the divided by the over dispersion parameter. And in this case, that would be 1 over 1 plus mu times Y in this case, mu times mu times Y, sorry, this is mu times Y. The formula is mu times Y. Remember, we don't have to worry about, because if you kind of look carefully in this formula that I provided earlier, neta is basically mu times L, right? So mu L will cancel out, and then you don't have to worry about the L, and then you will end up with just the equation 2, which is W equal to 1 over 1 plus mu times Y over the over dispersion parameter. Okay, so in this case, it will be mu, the number mu is 2.41 times Y is just 1 divided by 2.05. And you end up with a weight of, if you were to solve all of this, you end up with a weight of 0.46. Okay? So your weight will be 0.46. That's the weight you want to assign to your site estimate. Okay? And then once you figure out the weight, then it's pretty easy then to figure out how many crashes would you expect. So what you'll take is, you'll take the weight, and I want to try to write that down here on this page so that we can refer it back easily. Okay. So once you figure out that your weight is 0.46, all you need to do then is take weight 0.46, multiply that by 4.34, that's the number expected in 1 year period on that segment based on similar sites evidence, plus 1 minus weight, 1 minus 0.46, and you multiply that by 12. Okay, and then that will be your final answer. And if you were to solve that, you'll get a number between 4 and 12, which will be 8.48. Okay, so I see that there are some chat messages. Let me take a quick look at those. No, there are no more chat messages. That's good. So how did we get to this 8.48 number is the weight formula. And remember, the weight formula is coming from equation 2 of your paper. And I'm going to go, if you give me 1 second, I can go ahead and bring that equation 2 over so it's clearly written. I have that handy as well. So which equations did we make use of here from the tutorial? We made use of 2 different equations. Obviously, one was the equation 1, like where we figured out the estimate of the expected crashes for an entity, weight time crashes expected on similar entities, 1 minus weight time count of crashes. So that's your equation 1. We made use of that. And then once we did that, then we made use of equation 2 that's embedded into the actual example here. That's the equation 2 that we made use of. If you're looking at a segment, weight equal to 1 plus mu times y over phi. So those are the 2 really equations that you need. But just you have to remember, what is mu? Mu is the direct output for from your SPF. You don't multiply the length here because the length does cancel out based on the earlier formula that I showed you. And then capital Y is the number of years, and phi is the over dispersion parameter. Okay? So you are able to then get both of those things, and you get 8.48. And let's write down the unit for it. It's a good practice to write down the unit for it. So I'm going to write 1 unit, and you give me thumbs up or thumbs down based on whether or not this unit is correct. Okay. Crashes per kilometer a year. Give me a thumbs up or thumbs down whether or not this unit is correct. Okay, so there is no thumbs down. That's not good. I know why they don't have it. So give me, I don't know, give me the surprise icon if you, or answer yes or no in the chat box. That's fine. Give me whether or not anybody who thinks this unit is correct, give me a thumbs up. Let's go with this. Anybody who thinks this unit is correct, give me a thumbs up. I'm not seeing any thumbs up, which is a good sign, unless you have basically left your screens. Okay. So yeah, this unit is in fact not correct, because we have already, when we put in the number 4.34 and this number 12, that already accounts for the length of the segment. Okay, so this unit is not correct. So the unit actually should be 8.48 crashes, because remember, I already multiplied by 1 as well at the in the earlier number. When I did my neta in this one, I already did multiply. When I got to number 4.34, I did multiply, because in this example, you could say the unit could be crashes or crashes per year. They both will be correct here because the number of years in this example was just 1. Okay, and because the number of years in this example was just 1, both units, crashes or crashes per year, would be correct. Now let's do this example. But now I want to take the example of the same segment. So now I'll have the exact same segment. Okay, I'll have the exact same segment, same 1.8 kilometer segment. So I'm going to write that down, 1.8 kilometer segment. ADT of 4,000 vehicles per day. Okay. But now though, and my SPF is the same, and my SPF is still the same, and my over dispersion parameter is the same, and I'm going to write that down just so we have it for our reference, 0.0224 times ADT raised to power 0.564. Okay, so same ADT. Okay. And then once we have that, Hannah, I see your question in the chat box. I'm going to answer this in just 1 second. So let me just kind of have all the data down for this. So the only difference between this problem and last problem now is that instead of having just 1 year worth of crash data, I now have 3 years worth of crash data. So I have that 1 year worth of crash data for most listeners. It had 12 crashes. But then we also know, okay, and then we had 7 crashes. And then 7 crashes and 8 crashes. Okay, so now I have 3 numbers. So I had 12 crashes last year, just like in the previous example, but now I'm able to get 3 years worth of data that includes 7 crashes and 8 crashes. So now what I want you to do is replicate the problem, figure out how many crashes do I expect in a 3-year period. So now I know what is the expected crash counts for this segment over a 3-year period. Okay, so this is what I want to figure out. What is the expected crash count for this segment over a 3-year period? Okay, so I'm going to try to take Hannah's question here that she typed up in the chat box. So thank you for that. Since our weight was 0.6. Okay, so her question is, since our weight is 0.46, does that mean we shouldn't rely on crashes expected on similar entities? So our weight came out to be 0.46, and presumably I'm thinking that you mean it's less than 0.5. Yes, you are right. But remember what we are saying is that it doesn't mean that we are not saying we should rely. No, I think what we should do is, so your statement is, should we not rely on crashes expected on similar entities? No, we should rely on those, but we should rely on a mix of the evidence. And because I think our over dispersion parameter was high enough, that basically led to reduction of the weight. So if our model had a lower over dispersion parameter, if we had more precision in our model, then we could rely on the model's output more. But in this case, because our weight relies on the over dispersion parameter, the over dispersion parameter was such that our weight came out less than 0.5. So yes, we are still, even though we only had 1 year worth of crash data, our reliability of our safety performance function was such, based on the over dispersion parameter's value, was such that the weight still came out to be less than 0.5. So it's not to say that we shouldn't rely on one thing versus the other. The whole story is that we should combine the evidence with some statistically defensible weight, and that's what we are doing. So yes, so it's not a question of either or, it's a question of how much. So yes, we should give 46% of the weight to the entities, similar entities, and we should give 54% of the weight to our current entity. Okay, now what will happen is that in this example, and I think this will make it clear, based on how I have explained, can you take a guess on what do you think your weight will come out here as? Your over-dispersion parameter is the same, but now you have 3 years worth of crash history. What do you think should happen to your weight? Should the weight go up or down from the previous problem? Should the weight go up or down from the previous problem? In the previous problem, our weight came out to be 0.46. My question to you is, in this problem now, before doing any sort of calculations, what do you think should happen intuitively? What should happen to your weight that used to be 0.46 in the last problem? What would it be in this problem when now you have 3 years worth of history? The weight should go down is what I hear from Will. Emily says lower weight. That makes sense to me. And I hope it does to everybody, because now you have more crash history. And if you have more crash history, you want to give more weight to your own site. So weight should go down further. And that is exactly right. But let's see if we can, get a notepad out and try to see if you guys can work out the example one step ahead of me. So your first step is to estimate the mu. So let's see if you guys can estimate the mu value, just like we did in the previous problem. What do you think will mu value be for this problem? Having done the last problem, you should know what will be the mu value for this problem. The mu value for this problem, you shouldn't even need the calculator, because we basically did that. Because remember, the unit for mu is crashes per kilometer year. Yeah, that's right. So Will says 2.41. That's exactly right. But I will just kind of say that the units are not quite correct. It should be 2.41 crashes per kilometer year. So it's going to be 2.41 crashes per kilometer year. Okay, everybody clear on the units? That's good. Now, if I asked you, okay, if I want to find my neta in this problem, even though we don't need that necessarily for the weight, because the way we use the weight equation now, we don't need the neta, but we should be able to estimate that. Remember, that was the expected crash count for the years of analysis that you're using, the period of analysis. So what is the period of analysis in this example? The period of analysis in this example, it depends on how much crash data you have for your own entity. So that would be a 3-year period. So my period of analysis is 3 years. So I should be able to figure out my neta value based on neta is number of crashes in the analysis period. Okay. And that would be 2.41 times 1.8 times 3. Okay. The formula for that is mu times L times Y, the number of years. And I know my phi and y's are sort of messed up here, so my apologies for that. But because I'm talking and we are recording this, hopefully there's not a whole lot of confusion. So 2.141 times 1.8 times 3. So you would expect in 3-year period, you would expect, and I'm going to just use my calculator here. I hope some of you guys are one step ahead of me on this. So you get 13.014, and now the unit will be crashes. Okay, remember, I've already multiplied by the length, kilometers, and number of years, 3. So now kilometer year goes away from my units. So I should expect in 3-year period, if I'm just relying on the SPF, I should expect 13 crashes. Or you can say an entity similar to this would experience 13 crashes, 13.014 crashes in a 3-year period total. Okay. Now I need to figure out the weight here. Okay, I need to figure out what the weight is going to be. So remember my weight formula is W is equation 2, and I'm going to write that down here. My weight formula is 1 over 1 plus mu times y over 5. This is my weight formula. So why don't you guys go ahead and estimate the weight for me? Take 1 second here, or maybe another minute or so, and see if you guys can figure out the weight for me. If you have the weight, you can text it to me, 0.221. I hope you just didn't look that up from the tutorial. So 0.22 is correct. That's great. And I'm seeing some folks that are still doing it, but that's fine. But you could see it that it's going to be, it's lower than 0.46, so that's a good sign. So if you got a number that's more than 0.46, that should basically have your alarm bells ringing that, okay, yeah, that's not right. But so remember, that's going to be 1 over 1 plus mu is 2.41, and I multiply it by 3, and I divide by 5, which is 2.05, and then once I do that, 2.41 times 3 over 2.05, and this is the formula what I'm going to use. And remember, mu is always the direct output of the SPF. Y is the number of years, and you divide by the over dispersion parameter. Okay, so you got your W there. Okay, so now I know my weight. It's going to be 0.22. Now the question is, how do we estimate now the number of expected crashes on this entity? How do we get the number of expected crashes on this entity? Now I know the number will be somewhere between 13.014 and the 3-year crash counts that I observed, 12, 7, and 8. So that's about 27 crashes total. So basically what it's telling me is that my site is telling me that I should have 27 crashes. My SPF is telling me that I should have 13.014 crashes. How do I combine these two estimates? I combine that using this 0.22. That's the weight that I've estimated. Okay, so my expected crashes over a 3-year period will be, so I will just do 0.22 times 27 plus 0.78 times 13, and I can easily calculate that number. Okay, so I'm going to just use my calculator here, 0.22 times 27 plus 0.78 times 13.014, and I get a number 16.09 crashes. The unit will be just crashes, okay? Does that sound good? Any question about this? That is correct. Thank you, Jordan. Appreciate you paying attention. This time I really did it on purpose, okay? Yes, so this is not quite correct. This is not correct. Why is this not correct? Because my weight goes with the SPF estimate. So I should actually be doing not this. I should be applying 13 with my 0.22, and 27 should go, because I want to give more weight to my site's estimate now. Okay, so this is incorrect. So my number would be actually expected crashes over a 3-year period will be 0.22 times 13.01 plus 0.78 times 27. Okay, and where am I getting this 0.78 from? It's 1 minus 0.22. So yeah, thank you, Jordan, for paying attention. I hope some more of you caught that, but you just didn't type it up in chat. So does that make sense now? And then if you were to just apply the weighted average, what you'll get is a number that's much closer to 27. Okay, it'll be a number much closer to 27, and the number will be 23.92. Okay. So, and then the unit obviously would be just crashes here. Because I've already accounted for the 3-year period, I've already accounted for the number of years and the length of the segment. Now, one thing that I haven't yet talked about, and I think we should, is that anytime you're providing a statistical estimate, it's a good idea to give what we call an error bar or error estimate or a sigma value, a standard error estimate. And the standard error estimate is actually because is very, so sigma, we call it sigma of an estimate is basically square root of 1 minus weight times the estimate. Okay, 1 minus weight times the estimate. Okay. So if you know your weight, you can easily estimate the sigma value. So I want you to do is, I want you to take 1 minute and estimate the sigma based when we did the 1-year data. And I want you to estimate the sigma based on 3-year data. So I want you to estimate sigma values. I'm going to take a 1 minute break here. And I'll give you time to estimate the sigma value based on 1-year data and the sigma value based on 3-year data. Okay. So the formula is still the same, 1 minus weight times the estimate. So let's take a minute now to estimate these two values of sigma. 1 minus weight times the estimate. An estimate is your final answer that you got. Okay. So let's go ahead and estimate the weight value, 1 minus weight times the estimate, and see if we can do that. Okay, anybody has the number for the 1-year crash data? If I want to get this 1-year crash data, the value of sigma for the standard error bar, 1 minus weight times the estimate that will come from previous problem. Okay, 2.14 is one number I see. Okay, that's great. Thank you, Hannah. Okay, let's do it for crashes. And for 3-year data, I saw a number for 3-year data as well. 4.32. 4.32 crashes. Number will be the same. The unit will be just the crashes. So yes, so if you were to just apply the number 1 minus weight, so it will be for 3-year data, it will be 1 minus 0.22 times 23.92. So if you were to do that, so I'm just going to show you the calculations for the 3-year data. It will be 1 minus 0.22 times 23.92 and square root of the whole thing. And if you did that, you will get 4.31944 or something, which is basically 4.32 crashes. Okay. So that's how you do it, which is fine. Question for you. How come my 1 year estimate of sigma is lower. So I got a number 2.14 if I were just using the 1 year data, 4.32 when I was using the 3 year data. Shouldn't my standard error go down if I'm using more data? What is happening here? What is going on here that my standard error when I was using just 1 year worth of data was 2.14. When I use 3 years worth of data, now I'm at 4.32. What is going on here? Any thoughts on that? You could either raise your hand for chat or you can just type it up in the chat box, or you can raise your hand to talk. Any thoughts on why my number is for the standard error is higher when I'm using 3 years worth of data, and it's lower when I only use 1 year worth of data? What might be going on? Shouldn't the standard error go down if I use more data? Yes, so that's a good point. Like if your estimate is higher, means you have more crashes, means the sigma will be higher. So yes, exactly. So Jordan is exactly right. The standard error is smaller, not absolute value. Obviously, the absolute value of the standard error will go up because if you look at the formula for standard error, you can see as the estimate goes up, sigma will go up, right? The thing is that though, if you have a value, so you have to look at the standard error value not by itself, but in relation to the average, in relation to the estimate. So this 4.32 value. So the correct answer to the query that I posed to you is that sigma should be looked at in relation to number of crashes expected. So you're looking at sigma as a proportion of number of crashes expected. Yes, the value of the error will go down, but it will go lower as a percentage of the mean. Okay, and you can figure this out pretty easily. We had 4.32, but our estimate was 23.92, and we had an estimate of 2.14 when we were looking at, so sigma used to be 2.14. It used to be 2.14 and an estimate of 8.48, and now sigma in 3 years used to be 4.32 in relation to 23.92. So now if you calculate that as a proportion, you can clearly see that it's 4.32 divided by 23.92. That gives me about 18% error. And then if I do this, 2.14 divided by 8.48, that gives me about 25.32% error. Okay, so it goes down as a percentage of the mean, and that's the right way to look at standard error. Does it go down compared to the standard, compared to the mean? Okay, so any question about these two problems that we talked about in the in this lecture so far? Okay, perfect. So I'm not hearing any questions, which is great. So what I'll do now is that I'll give you one more tip first. And once I give you the tip, I will have you read through numerical example number 3. And then we'll take a little break at the same time. And then we'll go from there. Okay. So one tip I have is that sometimes your safety performance function, the equation that I provided to you, may not be directly applicable. because your own site's characteristics might be different compared to what you have, compared to the data that was used to estimate the safety performance function. So for example, in the next example that is in the tutorial, so let's say, so just to kind of pick up on that, so your safety performance function was given as mu equal to 0.0224 times ADT raised to power 0.564, right? That was your mu value. This was your SPF, the safety performance function. Now you learned that this safety performance function was estimated on a site, on a bunch of sites really, because this information is basically a negative binomial regression model. And we'll talk about that later on. But this regression model was estimated on sites, on roadway segments that all of them had 1.5 meter shoulder width. So all of these sites had 1.5 meter of shoulder. Okay? So there is some additional information about the sites where this SPF was estimated from. Now you are looking at a site, let's say the crash history that we're looking at is only, our site only has a shoulder width, and our site of interest has a shoulder width equal to 1.2 meter. So now our shoulder width is only 1.2 meters, but this data we know is coming from, this information is coming for the safety performance function is coming from place where the shoulder width used to be 1.5 meter on all those sites. Now our site only has 1.2 meter. So what I'm trying to tell you is that this SPF may not be directly applicable to our site. What do we do? What we do is we actually need to then account for crash modification factors. We need to account for this difference between our site and the sites where the SPF were estimated from. And this is where the concept of CMF comes in. What to do? We apply CMF. And what is a CMF? CMF is a crash modification factor. So I want to apply a crash modification factor to the mix. So where do I find CMF? Highway Safety Manual provides the CMF for a bunch of different factors. And we'll get to that point as well in the class. But for now, suffice it to say that this will be given for this module. Any problem that you do, I will be providing you with the crash modification factor that you need. So the crash modification factor for this example is, let's say, what is happening is that you are reducing the shoulder width by 0.3 meters, 1.5 versus 1.2. And typically, if you have shoulder width, narrower shoulders, you expect more crashes. And in this case, it is known that a shoulder width reduction of 0.3 meters will lead to crashes increasing by 4%. It is known that a shoulder width reduction of 0.3 meters will lead to a crash increase of 4%. So you can expect 4% more crashes. So my question to you is, based on this information, what do you think would be your CMF? You can either type it in the chat box or raise your hand to give me the answer. What is going to be my CMF based on this information? What is going to be my CMF based on this information? We know that a reduction of 0.3 meters in shoulder width leads to crash increase by 4%. So can you tell me what's going to be my CMF? Yeah, what's going to be my CMF? I see 1.04. Okay, I'm getting a little bit worried that I'm only getting answers from usual suspects now. I see Will's responding with 1.44, which is great. I appreciate that. I appreciate my usual suspects to respond because otherwise I'm just staring blank and nothing is happening. So it's great that you guys are responding, but I'm getting a little bit worried about that. So just a fair warning that I might actually start calling your name. And when we were doing in-person classes, I might have trouble remembering everybody's name, but now that we are online, I can see everybody's name. So I hope all of you are paying attention. It's just that you're too lazy to type up, or you're just not finding it accessible. So I might start calling out some names as well, just so we know that everybody's at least somewhat paying attention. So anyway, CMF is going to be 1.04 here, which is great. Then, if I'm using a CMF of 1.04, this changes the estimate that I get from SPF. Okay, crash modification factor, because an increase of 4%, the CMF would be 4.04. If a site with 1.5 meter shoulder would have had one crash, a site with 1.2 meter shoulder is expected to have 1.04 crashes. Okay? So that's the way you interpret the CMF. So using the CMF is pretty easy, pretty straightforward. You just basically, so your mu will be CMF multiplied by the SPF output. So your expected crashes will be, your mu in the example will be CMF multiplied by the output that you get from the safety performance function equation. That's all you need to worry about. Okay, and the rest of the problem remain the same. So what I will do is I will stop here, take a pause, and maybe take about 15-minute break here. And in that 15-minute break, first thing you should do is just kind of hang out, get some sun, step aside maybe for 5-7 minutes, and then look at the numerical example 3 on page 6 of the Howard tutorial. So to take a look at the page 6 of the Howard tutorial, there is a numerical example number 3. So take a look at that. In fact, try to work it out if you could, please. It basically relies on the safety performance function idea, and hopefully you guys can do that. So, and we will reconvene at about 9:50 a.m. Okay, so reconvene at 9:50, and I will go ahead and pause the recording unless there are some questions that you want to ask. So if there are no questions, we'll just take a quick break. And we'll come back at 9:50. Thank you. Okay, welcome back to CE 26. We're back from the break. We were talking about use of crash modification factor as you're applying the empirical based procedure. And I asked you to look at the problem number 3, or example number 3 in the Ezra Howard tutorial. And that's basically what it does. It applies the CMF. I hope you got a chance during the 15-minute break, you got at least a few minutes to look through the example. And I'm not going to go ahead and discuss that example completely. But one thing I would say is that I will just show you that example here on the screen. And what I'll show you is that what they did was they took the original example for 1, and then they just multiplied the SPF estimate, the mu value, with 1.04. So all you had to do was just take the mu and apply the CMF times SPF output. And that's exactly what they did. Okay, and then the procedure is fairly similar. Okay? Then the procedure is like, if it's 1.8 kilometers, and if it's a number of period analysis is 3 years, so you use 3 years, and then you estimate the weight. Weight goes a little bit lower here because weight goes a little bit lower because the mu value increases a little bit, and that causes the weight to go down a tiny bit. But anyway, and then you can just do the expected crashes, 0.214 times 13.55. That's 13.5 crashes from here. And then 0.786 times 12 plus 7 plus 8. And then the estimate comes out to be 24.12. Now, it's a similar problem. My question to you is, why was the crash modification not applied to these numbers? So see, we only applied the crash modification factor to 2.41, the SPF output. Why was there no 1.41 or CMF applied to the crash history of the site? See, this 1278, they're directly being multiplied by the weight value, or 1 minus weight value. Why is there no 1.04 factor applied to this 12, 7, and 8 number of crashes that you experienced on your site, the 27 crashes that you saw? Any thoughts on that? And just to sort of get away a little bit from my usual suspects, I'm going to try to pick a name here. Mikhail, do you have any thoughts on why I have no crash modification factor applied to history of my own site? Why don't I multiply these numbers, this 27, 12 plus 7 plus 8 with 1.04?
My initial thought would just be because it's already just flat out data that you've taken.
Right.
And then the other thing would just be if you were looking at the whole term for like 0.786 times that, or the weight multiplied by that data, the weight technically has the CMF built in with that 2.51 value.
So you're almost there. You're almost correct. The only thing I would say is that actually it's not the weight that has the CMF built in. Weight does have CMF incorporated in that. But the most important thing is that your site, the crashes that you're actually seeing on your site, it already is because of it has a lower shoulder, like a smaller shoulder, right? So your crash history automatically accounts for your site's characteristics. So that's why you never have to apply. If you actually are observing something on the same site that has those characteristics, you never have to apply the crash modification factor. It's only the data that was coming from 1.5 meter shoulder sites where you had to apply that CMF. Okay, and this is very similar to, if you recall, maybe from your CE 321 fundamentals of transportation class, you know how when we assume some free flow speed, then we sometimes have to, when we are given like a base free flow speed based on ideal condition, then we have to apply the factor. But if you go out to your own site and you collect the data, then you get the free flow speed directly. You don't have to apply any modifications to that measured free flow speed from your site. So think of it the same way, where crash history already is coming from place that has a 1.2 meter shoulder, so it does not need any more correction. Okay, so that's why that's basically I wanted to convey. So what I want to do next is I want to work on another example number 4. And example number 4 is interesting, and that happens in practice quite a bit when you're analyzing data, is that you will have different ADT for different segments of the road. and you will have maybe different characteristics because one site might have, like over a certain segment, it might have longer shoulder, over a certain segment, it might have shorter shoulders. So this happens quite a bit in real life practice. So then the question becomes, how do we account for the data that we have from multiple segments? If we have data from multiple segments, and all those segments have somewhat differing characteristics, and let's look at the characteristics of my site. And now my site is based off, it's separated out into 3 different sections, and I have these information about my site. So I have these subsections number 1, number 2, and number 3. They both have different lengths and different ADT. Okay. So I have a length of 2000, length of 2300, and then, length. Okay. So these are my ADTs. The ADTs are same for segment 2 and 3. And then the crash modification and the length of the segments is 0.1 kilometer, 1.2 kilometers, and 0.2 kilometers. And then I'm also given a CMF that's different because, and again, I'm not given the specific site characteristics that cause the CMF. I'm just provided with a CMF. And the CMF for this site is 0.90 for the first segment, 0.95 for the second segment, and 1.05 for the last segment. Okay. So now what do we do? So yeah, these are my characteristics. But my problem is, here is the problem. You could solve this problem as 3 different problems for segment 1, 2, and 3, but sometimes this could be a problem. The problem could be that you don't have the data that's precise enough to be divided into these segments of 0.1. Specifically, that would be a problem for these smaller segments. For this 0.1 and 0.2 miles, you don't have precise data that breaks itself down into these segments for your own crash history. Okay, so your crash history is a combined crash history for this 1.5 kilometer segment, and your crash history is given that, and it just says 11 crashes for the past, or not for the past, but over past 2 years. So 11 crashes over the past 2 years. And they're not broken down by these segments. It's just that over the 1.5 kilometer segment. So 11 crashes over the past 2 years over the whole 1.5 kilometer segment. So they don't break down the crash data into these entities. So what do we do? So the approach to doing that, and this happens in practice quite a bit, I can tell you from experience, and hopefully I will be able to arrange for a guest speaker who did this some of this work for one of our research projects recently, where we were looking for these estimates. So what do we do? Actually, what we do is not very complicated. What do we do is that we try to apply our CMFs and SPF information for individual segment, and then we combine that information. Okay, so basically what you do is you estimate your mu. You estimate your mu in crashes per kilometer a year. Then you estimate how many crashes you expect. How many crashes you expect in total. And then you add those crashes up over the 2-year period. And then you combine that with the estimate of 11 using the weight value. So let's see if we can implement that. So let's see if you guys can help me find the mu value And everybody should have your calculators out and see if you can get me the mu value for the first segment. And remember, my SPF is the same. My SPF is still the same. My SPF still remains to be 0.0224 times ADT raised to power 0.564. So my SPF is still the same. So I want to find out, okay, what is my mu value? And mu is defined as crashes per kilometer a year. That comes from my SPF. So let's just figure it out. So take next couple of minutes to try to figure out the mu value individually for each of these segments. So I'm going to do this, try to do the same thing on my calculator, but let's see. Okay, does anybody have the mu value for me for each of these segments? Yep, 1.466. And I'm going to just demonstrate the second one, just so we know. So SPF is 0.0224 times ADT is 2300, and then 0.564. And if you were to calculate that, you will get, and I'm just doing it in real time. So you get 1 point, so if you were to calculate that, you'll get like something like 1.763. But remember, that's not the value that goes in there. What is the value that go in there into the table here for mu? I multiply that by the CMF, because I do have a CMF here. And I'll get 1.6748. So I can write it down as 1.675. Okay. And then similarly, you can get the last one, 1.851. Everybody clear on how we are getting these mu values? Crashes per kilometer a year. So how many crashes would you expect in a 2-year period for this location? How many crashes would you expect in a 2-year period for this location? For the first one, let's find out for the first one. How many crashes per year for the first one? So you multiply by the length. And you multiply by number of years. So that's exactly right. So crashes that you would expect at this location would be 0.2932. And then similarly, you can find that for the other location, 4.020, and then 0.740. Okay, so I'm basically using this number and multiplying it by respective length. And once I have the multiplied by respective length, I'm multiplying by respective years, and I'm able to get the number of crashes. And if I add these numbers up, I can get the total number of crashes, about 5.054 crashes total. So in a 2-year period, I would expect 5.054 crashes total in 2-year period. Okay. Now your table, in just want to make a note here that the table in the tutorial has just crashes here, but this table should be corrected to say that this is per year. Okay, so I should note that this is per year number. What they're reporting in this table is per year number, because they do multiply it by 2 later on. Okay, so just make sure that you correct the table in the paper online. It should be per year in the tutorial. Okay. Now, if you have 5.054 for 2-year period from the SPF and CMF application, you just have to combine it with 11. But to be able to combine that, you do need the weight. Okay? You do need the weight for each of these numbers. And the weight can be found out using the equation 2 of our tutorial, which is weight equal to 1 over 1 plus mu times y over phi. Right? That makes sense? And that will be, in this case, equal to, remember, mu times y. Okay, mu times y here. What will be the number here that you want to use? What will be the number you want to use for mu here? Remember, you want to enter in crashes per kilometer when you find your W. So what will be the value for mu that should be used? And then Y will obviously be 2 because it's a 2-year data. So my question is, phi is still the same, 2.05. I'm missing a number right here. What should that number be? Okay, so if you could type it up in the chat box, what should I use the mu value to, what should I use as mu value here in this example? Okay, Alexander, you say 1.715. And where are you getting this from? Okay. I hope not directly from the tutorial that I just showed you. So can somebody try to explain where the 1.715 is coming from? That is, in fact, the right answer, probably, unless there is an error in the tutorial itself. But let's see, where are you getting that 1.715 from? Right. So crashes on the whole segment. Yeah. So this number, because remember the unit on mu is crashes per kilometer a year. Okay, crashes per kilometer a year. So mu is that you're going to put in this formula. It'll be 5.054. That is the crashes in 2 years. You divide that by 2, and you also divide that by 1.5. To get the mu value, you'll just do the number 5.054, the number of crashes in 2 years that you're expecting according to your SPF. You divide that by 2, and then you also divide that by the total length. And if you were to do this, 5.054 divided by 3, because that's what it is. No, I don't think I got quite that number. Is that a rounding error? 2.527. Okay, so I got this number to be 1.68 something, and that's the number I want to use. So there is some error somewhere here. So I got 2.527 divided by 1.5 is correct. So I got the number 1.68 instead. Is that right? Am I doing it correctly, or is somebody else got the 1.5?
I got that as well.
Okay, so that is the correct number. Yes, you're right. So then there is this error here that I want to correct, because I think they're explaining it correctly, but I think what they're doing is that they're making a mistake in terms of. So they got this number that we also have when we add those numbers up. So 2.527, and you divide by 2.57, divide by 1.5, you don't get 1.715. In fact, you get 1.685. Okay, so that's the number you want to use. So I will just use 1.685. And then let's figure out what the weight is going to be based on that number. So W is going to be 1 over 1 plus 1.685 into 2 divided by 2.05. Could somebody calculate that weight for me? Thank you, Brian, for that information. And let's get the weight going as well. This is interesting. Yep, 378. That's the weight I got as well. So that's correct, 0.378. So now all we have to do is, once we know the weight, we can figure out how many crashes to expect in the 2-year period. So I could do 0.378 multiplied by the SPF estimate. The SPF estimate was 5.054 plus 1 minus 0.378, which is 0.622 times 11. That makes sense? So my expected crashes would be this plus this. And if you were to calculate that, plus, I'm getting a number 8.753. So you would expect total 8.753 crashes in 2-year period. Okay. Does that make sense? Any questions about this? So if you happen to see segments where you don't have individually broken down crash data, you do your calculation, remember the definition of mu, okay? Remember the definition of expected crashes per kilometer a year. So you divide by number of years and number of kilometers, okay? And then you kind of use that information to get to the point where you're able to then estimate what that number looks like for mu, and then use that mu to estimate your weight. And once you have the weight in place, you can estimate the number of crashes. And in all of your estimates I have given you, you should always be able to estimate the standard error given the formula. So remember that all the time. Make sure you do that. So that will be important as well. Any questions about this? Okay, perfect. I'm not hearing any questions right now, which is great. Are there any questions about this at all? Make sure you note the correction on the paper, a couple of them. This is crashes per year. And then this number, the way I calculated it, I got 1.685. Okay, instead of 1.715. Okay. I'm just checking one more thing. Okay. All right, perfect. So no questions here. Okay, so I'm going to move on to the next example that I want to work on. I'm going to skip the number 5 because I think the number 5 example is not quite the latest sort of information on this. That's not how I want to calculate number 5. So I'm going to skip the crashes by severity example because I think there are a better way of doing that. So I'm going to skip on that. Number 5 example. I will leave you guys to work on number 6, but I will briefly explain that because number 6 is the only one that has intersection example in there. But remember, the only thing that's different in the intersection example is that there will be no length in the mix. Okay. So I hope you're still having the iPad as the pinned screen, so you could see what I'm referring to here. So we're going to skip number 5, and on number 6, we have a 3-legged ruler intersection. The mu is estimated by a safety performance function that includes ADT on the main line and ADT on the minor road as the variables. An estimate of phi is 1.96. That's your over dispersion parameter. Consider such an intersection. ADT main line is 4,520 and ADT on minor road is 230. The crash modification factor, CMF, to account for the difference from nominal conditions is 1.27. So you have a really high CMF of 1.27. So this means, and there were 7 crashes in 3-year period. Okay. So the problem is, like, it's very, very straightforward, very simple in nature. You know, all you have to do is just plug in the numbers. And then once you get the CMF go, like you get the SPF estimate that we got, crashes per year. Obviously, the length won't come into picture because we're talking about one intersection. So length goes away. 1.041 crashes per year. You multiply that by 1.27, which is your CMF. You get to 1.322. And then once you get 3-year number, you get 3.966. And all you need to then figure out is the weight. Weight is just going to be 1.322 times 3 divided by 1.96. And you get a 33% weight. Once you have the weight, you assign the weight to the SPF estimate and your own site's history. So 7 is 7 crashes in 3 years. That's your site's history. 3.966 is CMF estimate, and then you just do a weighted average, and then you can get the. So it's a very simple example, other than the fact that your CMF, your safety performance function or your SPF had information on ADT on both major and minor road. Okay, that was a quick one. Any questions about that? Okay, no questions I'm hearing here, so that's good. So number 6 is good. We'll skip number 7 as well. And now we want to talk a little bit about the full empirical based procedure and the abridged procedure that we've talked about so far. Now, one thing I do want to point out, if you dig deeper into the safety literature, okay, what I'm going to talk about in the coming examples, example number 8 and hopefully 9 and 10 and all that, okay, what I'm talking about is full empirical based procedure. There's a completely different beast called fully Bayesian analysis. We are not talking about this. We are talking about just the full empirical based procedure, which is a different thing than somebody you might hear fully Bayesian procedure. So that fully Bayesian is basically you simulate some data. It's a completely it's a completely different beast than what we're talking about fully empirical based procedure. Okay, fully empirical based procedure essentially accounts for the fact that you might have. So right now, what all we've done is like we always kind of treated the ADT to be always the same, right? But in this example now, the ADT might differ and other characteristics, other information that go into the safety performance function, they might differ as well. So the analysis becomes a little bit more complicated, but but the overall gist of the procedure remains the same. So let's talk a little bit about fully empirical based procedure and what it does. The full empirical based procedure is basically able to account for year-to-year changes in ADT and other variables. So if there has been any changes in the ADT over time, you are able to account for those. Okay. So let's try to account for the changing ADTs here. So here is our problem, and this time I'm going to do is like so it's the same roadway segment, 1.8 kilometer long, physically unchanged during the past 9 years, so it hasn't changed a whole lot. The ADT estimates and crash counts for each year are given in rows 2 and 3 of table 3. Okay, so what I'll do is I will just make sure that we can see the rows 2 and 3 of table 3. Okay. So I want to be able to show you that. Okay. So this is what the data looks like. When we do fully empirical based procedure, I have the data going from 1989 all the way through 1997. My ADT has been changing, and my crash count, of course, has been changing, and I have 74 crashes per year. Now, what we are learning here is that how do we account for this changing ADT over time into my model, into my whole analysis procedure? How do we account for the changing ADT in my analysis? Okay. So if your ADT has been changing, what you'll need to do is, first of all, your mu per year would be changing as well, right? So your crashes per year would be changing. So let's first figure out your mu value in crashes per kilometer year for each of these years. Okay, so I'm going to start with 1989, 90, 91, 92, 93, 94, 95, 96, and 97. So for each of these years, I should be able to estimate a mu per year. So my unit here is, so let's first estimate the mu in crashes per kilometer year. Could you do that for one of the years? I think one of these numbers, you should be able to get that fairly easy. Okay, so your ADT, you know, 4,500. So let's see if I can account for that number in my analysis. So I'm going to just use my calculator here. So I have 4,500 to be my ADT. So I'm going to do 0.0224 times 4,500. And I'm going to raise it to exponent 0.564. Is that right? 0.564, yeah. I get 2.57. What happened? Why am I not getting 2.446? So if I look at the table in the tutorial, that number here says 2.446. Why am I not getting 2.574? Any thoughts on that? Why my number, the number that is in the tutorial, it says 2.446, but when I use my calculator, I'm getting 2.574. What's accounting for that difference? Okay, what's accounting for that difference is you need to read the problem carefully. And we didn't talk about this line. Assume further that to convert from nominal to real conditions, the product of all AMFs, the crash modification factors in this case is 0.95. So there might be like more than one AMF or CMF rather for crash modification factor, and the resultant crash modification factor for your sites should be 0.95. So anything that you get from your SPF has to be multiplied by 0.95. So the way you get it done is that you multiply it by what you got from the CMF, you multiply that by 0.95, and you'll get 2.445 as your answer, or 2.4455. So they'll round up to 2.446. So what you can do then is that you can then fill out this complete table based on those numbers, 2.506, 2.624, 2.653, and so on and so forth. So the unit is very important to remember here, crashes per kilometer a year. And then how do you think I'm getting from 2.446 to 4.402? Can you tell me in chat, how would you go from 2.446 on the row 4 of this table to 4.402 in row 5 of this table? Expected crashes in 1 year, basically. So you get that by doing what? How do you go from row 4 of this table to row 5 of this table? What operation are you doing there? Multiply by the length is exactly right. Thank you, Simon. So multiply that by length, which is 1.8 kilometer in this example, and you will get to that number. So now you should be able to get the number for row number 5 of this table, all of these numbers. So you can pick out any number. If I pick a 2.710 multiplied by 1.8, I get 4.879, which is right here. Okay, so you can pick out any of these numbers. So you got crashes in 1 year period. Okay. Now remember this number 6, you don't directly get this. Number 6 is basically your final answer. Remember, this is expected annual crashes for the segment. That is your final answer, okay? So don't worry about it too much. That makes sense? Okay, so you don't worry about it too much. You haven't even gotten close to getting that value yet. Okay, so just make sure that you remember that you haven't gotten, so this 7.36, we haven't gotten close to calculating that. There's no one simple calculation that you can do on 4.402 and get to 7.36. You actually have to figure out the weight and then figure out, a lot of different things. So how do you figure out the weight? The weight formula is basically the same thing, except for the fact that you just take mu number for every year. Okay, you take the number for mu for every year, okay, and then you divide that by 5 here. Okay, so mu over the first year over to the last year, and then you'll get that number to get the weight. Okay, so mu per year, year over year, and then you get the mu year, and then once you get the mu value for summed up for all the different years now, and that way you can estimate the weight that you're going to be using. Okay, so the weight now, if you were to actually calculate this, is going to be, remember now, we are not just simply multiplying by the number of years, because every year the estimate is different. So instead of sort of just completely multiplying the number of years by 9, because we were assuming every year is the same as the past year in the previous example, so you don't get to multiply now, you get to add the mu year that you get from every year. Okay, so mu year that you get from every year, 2.446, 2.546, and all of these numbers, you just add them up. And that number add up to 23.781. In the previous example, what we would have done, your ADT value would have been assumed to be constant, and you would have just taken this 2.446 and multiply that by 9. Okay, now we're not doing that. Now, because our mu year changes from year to year, we need to get the weight by using equation 7, which is summing up the annual value that you're getting each year, and then you add those up. Okay, so that's the most important difference when you're trying to implement the full Bayesian procedure, because your mu value that comes out of SPF is different every year. You need to account for that. Does that make sense? Questions about this? Okay, let me see if there is some question on the chat here. So I'm not going to multiply by 9. Instead, I'm going to add the mu value that I'm getting in row 4. So I'm going to say add row number 4. Okay, so I'm just going to add row number 4, and that's 23.781 here. And I'm going to get my weight by doing 1 over 1 plus 23.781 divided by 2.05. The weight value is 0.0794. Pretty low value, right? Which makes sense because now you have 9 years worth of crash history. So you don't have to rely as much on your safety performance function. Your site history will give you pretty good numbers there. Okay? So I will be able to get a very low weight, and then I will be able to combine this value of 42.806 that I'm getting by adding expected crashes over the 9-year period. So this is my SPF estimate, and this is my site history. And I can apply the weight value of 0.0794 with 42.846. That's the sum. So just remember, what is this 42.846? This is sum of row number 5. So 0.0794 times sum of row number 5 plus 1 minus weight. This is just 1 minus weight times 74. 74 is the total number of crashes that you experienced on the site. And you're able to get that number. And obviously, because the weight of the SPF was so low, your number is very close to what your site's estimate was. And then you can estimate the standard error as well. That's fine. Okay. Does that make sense? Any questions about this? So the key difference is you cannot just multiply by the number of years as we did in the original formula, because every year's mu year changes because of the ADT differences. Okay? Other than that, the procedure is basically the same thing, and you're able to get that number. Okay. Now, one last thing that they're talking about is that, so this is based on a 9-year crash history. And again, you cannot just simply divide by 9 to get the expected number of crashes in each year, right? That's the problem with this, is that in previous example, I could do, okay, 71.52 divided by 9, I'll get an annual estimate. The problem is I can't quite do that now because every year ADT was different. So if I want to get like any 1 year's estimate, I need to do this. I need to kind of take the ratio of mu year over summation of mu year and then distribute my 71.52 based on this number. So for example, if you want to get the 1997 estimate, you can have it, you can estimate it using 71.52 times 2.710 divided by 23.78. And so let's see, if you're going for 1997, 2.710 divided by 23.781. So that's the ratio that you use then. Because out of the expected 23.781 crashes, 2.71 occurred in 1997. So that's the ratio you want to use if you want to divide a total of expected 71 crashes into 1 year, so then you'll get that number to be 8.15, and that's the number 8.15 that's shown in this table. Okay. So what I want you to do now is take a couple of minutes and answer this question for me. You have access to the tutorial. Estimate crashes in 1994. Okay, so I want you to estimate the crashes in 1994 that you will expect in this problem. Okay, so any questions here? So if you can do it, let's go ahead and do that. Estimate number of crashes in 1994. If you're not clear how to do that, let's let's just ask the question: what's causing the problem there? Okay, let's take a couple of minutes to do this. So remember, my full 9-year estimate of the crashes is 71.52. And I'm asking you, out of this expected count of 71.52, how many should be expected to occur in 1994? Remember, I want to take advantage of my full 9-year history. So I cannot simply use the number 8 and the number 2.710. Because that would mean, so I could basically replicate the first example. So one way of doing this would be just to do the example number 1 and use the data just from the year 1994, right? You have the ADT, you basically just repeat that example. What is the problem with that? As you're trying to calculate the 1994 numbers, think about why can't you just replicate example 1 here too? What's the problem with that? And if you're not sure how to do this, please see if you can give me a specific question about this. Okay. Okay, so I'm just going to try to call folks out now a little bit. Isabella, do you know how to estimate the number of crashes that you would expect in 1994 based on this problem?
I'm not sure.
Okay. Can you think about, could you do what we did for example number 1?
Initially I thought so, but I don't, yeah, I'm not sure.
So one way is that, yes, the answer to the question of 1994 number, and it's kind of basically taking the example 1 of this tutorial and doing that. It would not be necessarily completely wrong here, but the problem with that process be that you are not accounting for the 9 years worth of history to get a more precise estimate. You are just sort of using 1 year worth of data, and that would be the problem with it. Okay, so how do we do it? Is anybody wants to, who is able to do this? Can you raise your hand if you're in fact able to estimate the 1994 crashes according to the procedure we just learned? Anybody wants to raise their hand and let me know if they could actually do this? Okay, so I'm not seeing any hands raised either, which is fine because, okay, Mikhail tells me he can do it. That's great. So because there are so few hands raised, so what I'm going to do is I'm going to try to explain that real quick. So if I want to get that, so basically what we're trying to do is like, we're trying to get we're trying to get to this number in row 6. I'm basically asking you, how do we get 8.15? How are we getting to this 8.15 number? How do we get there? Okay. So what we are doing for that number is that we know that overall in the 9-year period, we are expecting 71.52 crashes. And now I want to figure out how many of those 71.52 crashes occur in 1994. So you could do that by multiplying the total number of crashes that you expect in 9 years. Now, if I were to get like any 1 year's estimate based on the problems that we've been doing so far, because our ADT value we assume to be constant, we will just divide this by 9, right? But we can't do that anymore because now we have annual data broken out. So what I'll do is I will rely on the estimate that I got previously that my mu per year for 1994 was 2.710. And my mu total for 9 years was 21.781. So I'm going to use that as my weight of how many crashes would occur in 1994. It'll be 2.710 divided by 23.781. Okay, and where am I getting those two numbers from? I'm getting 2.710 for 1994. So this is the year 94. And I look at the mu per year per kilometer year estimate for that one is 2.71. And total in the 9 year, I expect 23.781 crashes. So I take the same ratio of that and then use that ratio to get my number. And if I were to solve that, I'll get 8.15 crashes in 1994. Now I made, I picked out 1994 year in random. It just so happened to be the same as it had the same ADT number as 1997 here. So 1994 ADT and 1997 ADT were the exact same. So that's why my number 8.15 for 94 and 8.15 for 97 were also the exact same. Okay. So this way I can broke it apart into number of year estimate. If you were to just kind of do the estimate using example 1 and use the number 8 and 1 year estimate and use the 5400 ADT, you'll get a different number here. And that would be a problematic number. That would not be appropriate because you would not be using the data for any other year. Okay, so I want to just use like one more minute here and try to see if you guys could work out 1991 for me, next 5 minutes. So now let's work on. So 1991 crash estimate. And that 1991 crash estimate, I want you to estimate it using. So basically my question to you is, how do we get to this number 7.89? How do we get to this number 7.89? Let's take next 5 minutes to work this out. And we know the answer to this is 7.89, but how do we get there? Okay, so let's go ahead and give it 5 minutes and see if we can figure this out. If you are not sure, please ask me a question about that. I would really appreciate your question if you're not clear on how do we get to that number. Okay. How many of you are able to get to the number 8.15 using the procedure that we just described? Raise your hand, please. If you're able to do it, that's great. Thank you, Mikhail. Hannah, thank you. Jordan, thank you. Alexander, thank you. Emily, Katie as well, that's good. Seeing more and more hands being raised. Kat, okay. Brian, perfect, thank you. Any other folks? Okay, so for the folks who are still here, Simon and Tessa, Valerie, Tessa's raised her hand, that's great. Brian, Christopher, Cody, Anna, Leslie, and Simon. Brian, raise your hand, that's great, thank you. Okay, so it looks like everybody is able to do this. And just for kicks, I would like you to kind of think about this question. What happens if you were to just replicate your example one problem, right? So if you just replicate the example one process, what result do you get? And that'll be interesting to know as well. Okay, perfect. Thank you, Christopher. And Emily and Simon, I'm assuming you guys figured it out as well. You just kind of unraised your hand after that. Okay, that's frank. So it looks like all of you got it. That's great to know. And then, so now I have a couple more things to talk about. So last two examples. If there are any questions, yeah, you can unraise your hands now. Unless if there are any questions, please feel free to ask them in chat. Otherwise, I'll move on to the last two examples here. So last two examples are analyzing or accounting for secular trends. Now, what we assumed there is that the only thing that was changing over a period of from 1999 to 1997, the only thing that was changing was ADT, right? That was our assumption there. Right? So now what we're trying to do, yeah, if you don't have any questions, you can unraise your hand for the last question, but if you do have some questions, keep them raised. So I'm just confirming that Megan, Chan, William, and Brian, you guys don't have any other questions. Okay, perfect. Thank you. Okay. So the last thing I'm trying to ascertain here is that, last couple of things, is that sometimes you could have safety change because of other things. You know, maybe the vehicles are certainly getting better. Maybe the drivers are getting more distracted, or you know, weather was bad one year, a lot of rainstorms or something that led to more crashes or something like that. So one thing that could be happening is you might have a secular trend in your region where you're trying to analyze your location, and where, let's say you're talking about a city of San Luis Obispo, and you're interested in one particular location, but you also know of the overall crash trends in that city or in that county or in that state, okay? Because of all these factors like weather patterns and so forth. So you could find what we call an yearly multiplier. An yearly multiplier is just an accounting factor for some secular change in crashes compared to 1989. So that secular trend is expressed using yearly multipliers. And how you obtain that is typically you compare the aggregate number of crashes that happened in your city or your county compared to 1989. So if your number went up, you have a factor. So 1990 had a multiplier of 0.984. That means that your county had, or your city had, a 2.06% reduction in crashes. In 91, the multiplier is 1.053. That means your county overall had a 5.3% increase in crashes. Okay, something like that. I'm sorry, it's 0.53% increase in 92. And in 92, you had a 0.5% increase in crashes. And that's why the yearly multiplier of 1.005 is used. So anytime you see fewer crashes than 91 in your city or your county, you had a multiplier that's less than 1. And if you see more crashes, and then for that year, you have a multiplier of 1.053. And how do these multipliers work? They pretty much work like a crash modification factor. So there was an increase in 1.6%. Okay. So if there was an increase in 1.6%, you just basically have a factor of 0.984. Okay. So that's how the yearly multiplier is estimated. Okay. So if you had a crash increase by 1.6%, you have your crash multiplier to be 0.984. Okay. And so on and so forth. So all you do is that they work very similarly to, and if you do any problem in this vein, you will be given a multiplier for this. They work like crash modification factor, so you just multiply it to that number. So obviously this number was the same 2.446, but once you apply the 4700 number, so you will see that this 2.446 or 466 number, it will be slightly different than what you saw in your previous example. In the previous example, that number used to be, so this number in the previous example used to be 2.506. So this number used to be 2.506, but you multiply that number by 0.984. So if you were to do 2.506 and multiply that by 0.984, you will get 2.466. So this is the number you get, 2.466. I don't know if you're able to see the calculator, but this is the number you get. So that's how you, so all you do is, only thing that changes in this example to the next is that row 4 now applies or now accounts for. So only thing that's different is that row number 4 accounts for the yearly multiplier. Okay, everything else is exactly the same. Does that make sense? Any questions about this? Okay. So what I'll do is I will stop here and I will have an assigned homework for you based on this problem that will be due on next Monday before the class. So there is not going to be any reading assignment for you, but there will be a homework based on this tutorial that we learned today so that you can work out like maybe 3 or 4 problems. They will be based on different examples that we covered in the class. And I will probably take like a few minutes in the next lab to wrap up this projection issue. It's a simple issue, but I don't think I can kind of wrap it up in 5 minutes, because I think there is what needs to be learned is that why do we need the projection idea in the mix? So I'll take some time to discuss that on Thursday. However, my point right now is that you should review these examples and work out the homework problems that I'm going to assign to you. And with that, I'm just going to stop our discussion. If you guys have any questions, feel free to stick around for next 5 minutes or so. And if you have any questions about the lab, I can try to answer that in the next 5 minutes. Otherwise, I will have office hours tomorrow from 8 to 10. So feel free to stop by then as well. And if those office hours don't work with you, work with your schedule, feel free to set up a calendar meeting with me. And calendar meeting, you can get that meeting with me using the Calendly link. So if you want to set up another time to meet, you can do so on this meeting link. Okay. So with that, I'm just going to stop here unless you guys have any questions. If you don't have any questions, you're free to leave. But if you have any questions about the lab or any of the things that we discussed here today, feel free to chime in and ask.
Are you gonna upload your written notes? Because I think it's possible that the recording is recording the speaker and not the iPad.
Oh, I think if I pin it, does it not record my pin?
I'm not sure.
Okay, I will.
I'm saying it's a possibility.
Okay, that's a good point. So what I will do is I will send the annotated notes that I covered today, and I'll scan those over as well. So I will do that.
Okay, thank you.
If the recording doesn't record it, and that'll be a big bummer if it doesn't happen. So I'll make sure that it does. Thank you. Thank you for letting me know, Simon. Okay. Any other questions? If there are no questions, you're free to leave.